Okay, yeah, we took the sideways detour into plane equations and projections, but I want to go back to the cross product, right? So let me share this. So, all right, so here was the cross product definition, right? And in, I think last Wednesday in groups, I had you guys playing around with this with some examples just to see how it works. But it's this weird equation here with the, you know, the V2W3s, the V3W1, the V1W2. And we also have this geometric definition, which is going to be very important to remember that it's perpendicular. It's a vector for us to remember. It's a vector, and that it's perpendicular to both of the given vectors. So let me write some stuff on the board. Okay, so yeah, so we have the dot product V dot W, which is a number, right? It's a scalar. It's a number, whereas the cross product is written this way, and it's another vector. Like I think I've said that sometimes the dot product is called the scalar product, and sometimes the cross product is called the vector product. And also that this can work in any dimension. I can take, you know, two 7-dimensional vectors, but this is specifically a 3-dimensional construction, because there's if you have 3 dimensions, if you have 2 dimensions, if you have 2 vectors, there's no direction perpendicular to both, right? I mean, sometimes there are times in math where people talk about a 2D cross product, and you're supposed to just think of it as like, then it's like not even a vector really, because it's supposed to be perpendicular, but maybe the magnitude of it still can be thought of as the area of the parallelogram as given like right here. But so mainly when we talk about cross products, we really just mean 3D. Okay, so that's a vector, and then we had this algebraic definition. Maybe I'll just write these again. Algebraic definition. Remember, I sort of gave it last time as this. I guess I should write what these vectors are. I gave it last Wednesday as this 3 by 3 determinant. So if we write these vectors this way as components, you know, as a sub 1, sub 2, sub 3 components, then we said, I mean, you should have this in your notes already, but we said that this is given by this 3 by 3 determinant here, where you put ijk in the first row, you put the components of v in the second row, and you put the components of w in the third row. And we can write this in terms of these 2 by 2 determinants. There's a minus sign here in front of the j. And then there's, I guess, yeah, v1, v2, w1, w2. Okay, sorry, I put these a little crunched together because I'm trying to fit it on the board. Okay, and remember that this 2 by 2 determinant is really, I mean, I could write it even one more time as just expanding out these determinants. And I'll keep the minus sign here. I know I have the plus sign on the handout, but it's sort of helpful to remember this. And then V1W2 minus V2W1 K, right? So this is the formula. Just wanted to remind you of all that. And then there's the geometric definition, which is that, but notice, because it's a vector, if we're If we're going to give a geometric definition, we need two aspects to it. We need magnitude and direction. Dot product geometric description was a number, so it's just a number, right? This was the length. This is the magnitude of A times the magnitude of B times the cosine of the angle between them. This one we have to give it as two separate things. We need the direction and the magnitude. So the direction is perpendicular to V and W by the right-hand rule, right? Because there's two perpendicular directions. And the magnitude, which is kind of strange, and we'll give another formula in a moment, is the area of the parallelogram formed by V and W. Okay. Like it's in the picture on the handout, but it's a little bit, it's a strange idea that somehow that this formula gives these two things, right? That we're saying that these are equivalent. Okay. And like I said, I let you guys practice a little bit, play around with it. And you see, wait, I want to do it down here. I'll just share screen again. So, you know, I had you compute V cross U, W cross U, check that it is actually perpendicular to each of these, to both V and U, which is kind of nice that it works out. It's anti-commutative. It distributes over addition. You can move scalars around. These are all things that you can do. Not super surprising, but it just behaves nicely, kind of like a multiplication does. Dot product had these same two properties, right? But let's talk about the general. I kind of want to give some of these general things here. So, for example, if we wanted to show that V cross W is perpendicular to both V and W in general. So let me go back to the chalkboard here. So some general properties of the cross product. It's kind of fun to check. I don't know, this is my definition of fun, which is, I know, a little bizarre, but checking things like this, that V cross W is perpendicular to V and to W. So properties of the cross product. So so here's one, is that V cross W is perpendicular to V, perpendicular to W. Of course, that's the definition in terms of the geometric definition, like that's by definition. But I want to check the algebraic, check that the algebraic definition shows this, check that this holds. This holds under the algebraic definition. So let's actually think about, let's just do V. W is going to be the same, you'll see. So this is going to take something to write out. But we want to actually check that this dot product right here, that if I do V cross W and I dot it with V, we want this to equal 0, right? That's what we want. We want that to equal 0. To be, if these two vectors are perpendicular, their dot product should be 0. Yeah? So let's just write it out. So I'm going to write out the algebraic definition dot with V. So let's do it. We can do this, right? We're smart people. I might put the V in front. It doesn't really matter. Just looks a little nicer, I think, algebraically, if we put the V first and then dot it with V cross W. Right, so V, and I'm going to let you guys do this and get ahead of me, but we're going to dot with, so I'm going to copy this formula down. Minus, yeah. math, you just have to be willing to just write things down over and over again until it's almost like in your muscle memory of your hand. Minus V2. Okay, so remember to dot this out, you're going to multiply the x components, multiply the y components, multiply the z components, and add them all up. So take a minute and do this. I want you guys to do it first, not just watch me do it. Take a minute to do this. Because I claim you're going to get 0, and it might actually even start to show you how one might come up with the algebraic definition of the cross product, because it sort of works out perfectly. So start dotting this out, right? You're going to multiply v1 times this expression plus v2 times this expression plus v3 times this expression. You're going to have a lot of letters floating around, but I claim it's going to, nice things are going to happen. Looks like a pencil, yet it's an iPad style. That's very exciting. Oh. You guys get what I'm asking you to do? Look at your lift ticket on your back jacket right there. Anything good happening? A lot of letters. I'll write out the first step. So if you finish this quickly, you could check W also, that it dots with W to equal 0. One nod. Is this working out to be 0? Feel the thrill of excitement rustling through the room as people are realizing it works out to be 0. No thrill of excitement. Is it working out? Oh, sorry. I was a slow writer in classes too. So. Okay, so I'm just going to start multiplying this out. We're going to get 6 expressions, right? Isn't the most fun thing in the world, but it's not bad. This isn't going to equal 0. This is 6, like super random. Do things cancel? V1, V2, W3 minus V2, V1, W3. Those cancel. V1, V3, W2. Is there a V1, V? That's with a minus sign. V1, V3, W2. Those cancel. And hopefully these last two cancel. V2, V3, W1, V3, V2, W1, minus sign. Okay, so that does equal 0. Yay. Okay. So, right, you get everything cancels perfectly, which is kind of weird, kind of interesting. If you try it with W also, I'm not going to do it because it, yeah, but you can try it with W, that it also cancels. And yeah, somehow it's like these things are set up perfectly so that when you do dot them with W and V, they exactly sort of create cancellation. So sort of interesting, the construction of these expressions. That's somehow that's possible to do. So I'll just say similarly for W dot V cross W. That also will give 0. Shouldn't believe me though, you should do it on your own. Okay, so they really are perpendicular. That's exciting. Maybe I won't write this all out, but you can check pretty quickly that you get this anti-commutativity property that V cross W is negative W cross V. If you just look at the definition, here. If you look at the definition, if you switch the role of V and W everywhere, like here, if I switched V and W, I would get W2 V3 minus W3 V2. That's exactly the negative, right? You're basically swapping these two terms. So yeah, so similarly, you can check that it's anti-commutative, which remember I said is a weird idea. Like we're not used to that in math, of the order, actually the order of an operation mattering, whether you do first times second or second times first. If you've seen matrix multiplication, that also happens there, but so 2 W cross V is negative V cross W. Just say check the algebraic definition, it's pretty easy. Geometric definition also says that because the way the right-hand rule works, right? If you swap the two, right, you're supposed to curl from the first vector to the second, curl your fingers, and then your thumb points a certain way. So if I swap the order of the two vectors, I have to turn my hand over and curl, and then my thumb points the other way. So that agrees. Oh, I guess I said that right there in part C of on the handout. Also that V, oh, that's kind of interesting that I don't think I've said this explicitly, that V cross V is 0, the 0 vector. You can see in the definition, the algebraic definition, right, that if you make V and W the same thing, then everything's going to cancel out. And another reason you might think why this is good is because if I take, how could I do geometrically the cross product of the same vector? What direction is perpendicular to a vector in itself? In 3D, how many directions are perpendicular to a given vector? 2? Infinite? If I just have one vector, right? If I have two vectors, there's two different directions perpendicular. But if I have one vector in 3D, there's a whole range of vector perpendicular. So it'd be hard to pick out like what the actual perpendicular vector is. So instead, it just works out to be 0. So, and also the magnitude. Think about this, like we've had for V cross W, we sort of said, well, there's this parallelogram they form, right? And the magnitude of V cross W is supposed to be this, is this area. But what if I have the same vector? Like if V equaled W, they don't really form a parallelogram, right? They sort of form like a degenerate, like they're, you know, it's almost like if I swept W down and it became V, the parallelogram would get smaller and smaller and eventually cease to exist. So V area of parallelogram formed by V and V. Well, no parallelogram at all, so it's 0. Parallelogram at all. So area equals 0. So you can sort of check that these properties both make sense algebraically and make sense from the geometric point of view. Okay. Questions about that? Any of that? Cross product is a little bit weird. Okay, another property is this one in number 15 that there's another formula for the magnitude of V cross W. In fact, if I draw this parallelogram again, let me draw it again. So that's V. Let me just draw it so that's like horizontal and W is like this. Maybe. And then we have this parallelogram formed by them. What is the area of a parallelogram? Like the old geometry way. How do you find the area of a parallelogram? Yeah. Well, yeah, but I'm asking for like just basic geometry, not like magnitude, not like a cross product. And well, why? Why is the sine theta there? What's the like? Just what's the formula of it? Yeah. It's base times height, right? Because it's like the rectangle. Yeah, I think you're getting ahead of it, but it's like the rectangle. It's like one thing you can do is you can chop this triangle off here and put it there, and you can see that it's the same area. So the area is just base times height. But the claim is that, so like, yeah, so area is base times height. But what's the base? The base is, like you were saying, the magnitude of V, right? Do you guys agree with that? This length right here is magnitude of V. And what's the height, especially if I draw it like here? And it says something about the angle right here. You guys see how this is going to work out? This length is magnitude of W. So the hypotenuse magnitude of W, so what's the height? How do we do it? I have a triangle with hypotenuse that and angle that. What's the height? What do we multiply by? Yeah, that to get from this length to this length, you multiply by sine theta, right? Because sine theta is opposite over hypotenuse. So opposite is hypotenuse times sine of theta. Yeah. So this height, this right here is actually, this length is hypotenuse times sine of theta. Right, that's what the usefulness of sine and cosine is. Like this base was cosine of theta. We actually used that when we were talking about projections, right? That we take the hypotenuse times cosine theta would give us this length of the base of this triangle, and times sine theta gives us the height of the triangle. So we basically get immediately that this is times magnitude of W sine theta. It's also worth noting that sine theta is always positive from 0 to 180. So that this is always a positive number, so it can be an area. Like cosine could have been negative, so dot products can be positive or negative. But magnitudes are always positive, so this better be a positive number. And that's okay because this is always positive because this angle is between 0 and 180. Yeah? i.e., the magnitude, because the definition of the magnitude is that it's the area of this parallelogram. We get this other formula And I'll just say you could compare. I mean, it's worth noting that this looks very similar to our dot product formula. So it kind of pairs nicely with the dot product in a certain sense, right? That we have this formula for the dot product. We have this formula, I was going to say for the cross product, that's a little imprecise because it's for the magnitude of the cross product. It's important that you put the magnitude here. You don't just put v cross w equals this, because the cross product's a vector and this is a number. Yeah. Anyways, that's kind of nice. That also fits with this. This also fits with the one above that, like, if v and w are the same vector, then the angle between them is 0. Sine of 0 is 0, right? So all the pieces fit together nicely. Okay. Any questions about any of that? You guys all seem very like, yeah, okay, whatever, King. Okay. Oh, the one last property is just this, what's on number 16 on the handout there, that like, there's this nice, like, I don't know, this weird, like non-transitivity or something. Like, I had this, and I thought this metaphor yesterday when I was like typing some notes for myself, that like, it's like rock, paper, scissors. Like what? Paper beats rock and rock beats scissors, but it's not transitive. Rock doesn't beat, what did I just say? Paper doesn't beat scissors. Paper beats rock, rock beats scissors, but paper doesn't beat scissors, right? Scissors beats paper. So you get this kind of like looping effect. There's something similar here that if you look at I, J, and K, I mean, you could check this with the, algebraic, you could do this with the algebraic formula if you wanted to compute I cross J. You could use 1, 0, 0 cross 0, 1, 0, and see that you get, I claim you get 0, 0, 1. You can check that. But also, you just want to think in terms of the right-hand rule. If we want to think geometrically, there's I, there's J, there's K, right? So according to the geometric definition, first off, what's the magnitude of I cross J according to the geometric definition? What does it say? What area would we be looking at? Yeah. Yeah, why 1? Yeah, it's really this square really in the xy plane that we're looking at, right? So you're saying like the magnitude is the area of this right here, which is 1. So magnitude is 1. And the direction is the right-hand rule, right? I stick my fingers in the direction of I and I curl towards J. Stick my fingers in the direction, you know, I is supposed to really be coming straight out the board at you. So I cross J, there's my thumb, is K. And then, yeah, the right-hand rule says, the direction is the K direction, but it's length 1, so it really just is K. It's not like if it was length, if the magnitude was 2, the answer would be 2K, right? 2K would be the cross product, but the magnitude is 1, so it's just 1K. Thus, I cross J equals K. And now if you think about And if you think about j cross I, right? J cross I, you have to stick your fingers in that direction and curl them in this direction towards, because that's the j direction. In this room, that's the I direction. That's the j direction. That's the k direction. So I cross j is k. J cross I, negative k, right? So that shows the anti-commutativity. What about j cross k? So stick your fingers in the j, that's the j direction, that's the k direction. Stick your fingers in the j direction and curl them towards the k direction. Yeah? You agree? I. So j cross k is I. J cross k, I. Getting some weird side eye from certain people in the room. Is that okay? Any questions about? You okay back there? Okay. You were looking at me weird. I can only see the eyes. I'm trying to go with what I have. Yeah. Okay. So which hand are you using? He was using his left hand, which is good. See, so I think I was saying this earlier that I'm lucky because I'm a lefty, so I can write and still do the right hand rule with my other hand. But you guys have to actually put the pin down and then do the right hand rule. Those of you righties. Good, right? So you got to use. Okay, so good. So J cross K, you agree you get I? And again, the area is 1 because the area formed by the J and K is just a square, side length 1. So similarly, J cross K is I. And then the one that's a little bit weird is the combination of I and K. Like, what if we did I cross K? Like, if we leave things in alphabetical order. What's I cross K? Yeah. Negative J, it looks like, because I stick my fingers in the I direction and I want to curl in the K direction. So that's that way. So I got to turn my hand and curl that way. But now I'm sticking in the negative J direction, right? So check, careful. I cross K is actually negative J. So if you want positive J, you have to do K cross I. K cross I. Now I'm sticking in the J direction. So, so in fact, this is what I'm saying, where it's really like, it's almost like the way I think about it is like, here's I almost think about like making a circle. I really should just make that circle, honestly, but I don't know why maybe I should just use I, J, and K are in a circle like that already. Like, so I think of like, oh, okay, I cross J is K, J cross K is I, and K cross I is J. But they kind of go in that direction. Right. That's my little like picture of this in my head. Relationship. So yeah, I'll just write that again over here. I cross J is K. J cross K is I. K cross I. I don't know if my rock, paper, scissors metaphor really makes sense, but hopefully you see some connection, some vague connection. By the way, this is something that I think it's fascinating to me about their, and it actually kind of shows you in some sense, oh, I've erased it, but the minus sign in the definition of the cross product, that one in the middle, that kind of throws everyone off, that minus sign in the middle. It's almost like explained by this, because you would think at the X, Y, and Z axes would all have a perfect symmetry, right? That like, because think about it, if we have X, Y, the X, Y plane, like if I draw the X, Y plane, this is something that's kind of my own little personal bugaboo that I like to say. Can you see me if I draw over here? Okay, so like, if you draw the X and Y axes like this, the Z points right out at your face, right? If I draw the Y and the Z axes like this, the X points right out at your face. But if I draw the X and the Z axes like that, Do you see where the positive y-axis is? It's actually the other way. It's in the board. So there's some weird, like, it's actually better to draw the z-axis here and the x-axis here. We talked about the xz plane. We really should call it the zx plane. And then the y-axis sticks out this way. The positive y-axis. I mean, obviously the y-axis goes both ways, but the positive y-axis sticks out this way. So it's like kind of like the thing that's kind of interesting today. It's really zx. Okay. We're good? All right. Now the one thing I wanted to do, I sort of teased this maybe at the end of class or last time, or when we were talking about planes last time, that I claim now that if I give you 3 points in space, you can find the equation of the plane containing them. That's the last thing I want to do with cross products. Then we can start calculus. We can move on to differential calculus. We've sort of done all the pre-calculus work we need to do. Okay, so sort of a slightly change in topic. So given 3 points in space, find the equation of the plane containing them. Okay, so let me just sort of draw a schematic of a plane. It's supposed to be a plane in space. And I have 3 points, you know, P, Q, and R in this plane. What we sort of said last time is that 3 points gives us 2 vectors. So we can call this V and this W. Right, so set V to be the vector from P to Q, set W to be the vector from P to R. And then the cool thing is that, like, now if you take the cross product of V and W, so these are parallel to the plane, right? Or really they're like in the plane, but they're, since they're displacement vectors, they're parallel. The plane. This is all happening in the plane, right? So what happens when you take V cross W? We get a vector perpendicular to the plane. So V cross W is like perpendicular to the plane. It's supposed to be a perpendicular. So N is V cross W. So, right. N equals V cross W is normal vector. And remember, just remember that, and recall, in the plane equation, A times X minus X naught plus B times Y minus Y naught plus C times Z minus Z naught equals 0. In this, the vector N, the coefficients of X, Y, and Z make your normal vector. So that means if we can find a normal vector, we can write down the equation of the plane, right? If we can find an ABC, then we can just write down the equation of the plane immediately. Yeah. Right here? Well, the way this is set up is that, you're right, I could have AX plus BY plus CZ equals D. But this is like a point, this is like a point version of the formula where X naught, Y naught, and Z naught is a point on the plane. So if you plug in X naught here, Y naught here, and Z naught here, everything cancels and you get 0. But you're right, I should say like X naught, Y naught, Z naught is a point on the plane. And the reason that worked is because the vector formed by these 3 things is also parallel to the plane, because if x, y, and z, if the point x, y, z lies in the plane, then you got 2 points in the plane and their vector is parallel to the plane. And that's why this formula worked, because this is, we remember we interpreted this as like a dot product, as the dot product of the ABC vector with this vector. And since one was in the plane, the other is perpendicular. Good, thank you. Okay, so let's do this. We got 10 minutes. I think we can do this. Give me a point in space. 257. Love it. Let's do P is 257. Who else wants to give me a point? Yes, negative. Good. Q is 3, 8, negative 4. All right. Who else wants to give me a point? Negative 429. Okay. We are going to find the equation of the plane that contains all these 3 points. Right? So let's just do PQ and PR. We could do any two of the ones. We could do QR or something. So what is P to Q? To go from P to Q, you have to add 1, 3 minus 2. So that's 1I plus 3J minus 3K. Is that right? Did I do that right? No, I didn't do that right at all. 7 to minus 4 is minus 11, right? Minus 4 minus 7. What is PR? 3 to minus 4 is minus 7. 8 to 2 is minus 6. Negative 4 to 9 is plus 13. Oh, I just did QR. You're right. Thank you. Turns out it would have been okay because it's any two of them, but thank you. 2 to minus 4 is negative 6. 5 to 2 is minus 3. And 7 to 9 is plus 2. Oh, that's a little bit of a nicer vector. Good. Thank you. Yes, catch me when I do stuff like that, please. Did I do that right? Oh, hey, cross product them. You guys do this. You have the formula for the cross product. Take the cross product. It's supposed to be perpendicular. So I'll give you guys a minute. Check with your neighbors. If you get good at this, you can start doing it just from this. You know, if you sort of start to remember, oh, like for the I component, I need to cover these up and do this 2x2 determinant. Ooh, good numbers here. So hopefully I copied this correctly and .33s and 66s floating around here. Picking the points randomly means the equation may not be that nice. But again, it's kind of satisfied when we check that all these points satisfy the equation that we come up with. What's up? You're shaking your head. It's just a ugly vector. So what are people getting for the x component? The I component? Negative 27, the 6 minus 33, minus negative, 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 minus negative, negative. This is negative times negative, so that's actually positive. So 6 minus 33 is minus 27i minus this 2 by 2 determinant, right? What do you get there? Anybody get that one? Anybody else? Or am I getting too far ahead? Negative 64. So 2 minus 66 is negative 64, but there's a negative sign, so this is really plus 64j. And then the k component. Anybody got the k component? Minus, wait, this is minus 3 minus negative 18. Is that right? 15 plus 15k? So easy to mess these up. Okay. Oh no, this, okay, I thought maybe there was something we could, okay, so that is supposedly our normal vector, right? And then we could use one of the points. So these are the coefficients of x, y, and z, right? Coefficients of x, y, and z, respectively. And we can use one of the points, say P. Use P, it doesn't really matter, it's going to turn out, but we could use any one of the points and say that we get minus 27 times x minus 2, because that comes from P, plus 64 times y minus 5, plus 15 times z minus 7 equals 0 is supposedly the equation of our plane. We can sort of simplify this and do ax plus by plus cz equals a constant, minus 27x plus 54 plus 64y minus 320. I'll do this kind of quickly just because we're going to run, I don't want to run out of time. Minus 105. Woo. So this is plus, so we get minus 27x plus 64y plus 15z, and I get maybe 371 here, but I could be wrong. Is that right? I just rearranged and did numbers. But the real reason, I hope this is right. The real reason is I want to plug each of these 3 points in and see if they satisfy it, because that's the whole point, right? We're trying to find an equation that contains all 3 of these points. So just in the last couple minutes, you 2 columns, plug in point P, make sure it satisfies that equation. You 3 columns in the middle, plug in point Q, see if it satisfies that equation. And you 3 columns over here, plug in point R, to see if it satisfies that equation. It's some numbers, but if it works, then it's supposed to satisfy all 3. All 3 points are supposed to satisfy this, right? Uh, 64 times 8 is 512. Oh my God, there's some ugly. You might need a calculator to do this, or write by hand or something. What's that? R does work. R works. Q works. And P works. Yes. It's kind of crazy, right? So just if you haven't, just check that P, Q, and R all satisfy this. So this process does work. All right. So kind of cool. Kind of neat that you can find the equation containing 3 random points. Didn't say it was nice, but it does work. And it's the one equation that does that. All right. Yeah, if you're not sure about any of this, please come talk to me, office hours or whatever, or just go through your notes and see. But all right, so I have office hours, homework for Tuesday. I'll post homework for Friday. Keep on trucking. All right, thanks everyone. Go ahead.